All right, let's talk about cryptography. It's this invisible shield that's constantly protecting your messages, your money, your entire digital life. So let's dive right in. Every single time you send a text or buy something online, there's this silent guardian working in the background. But what is it really? How does it take your private info and just scramble it into total gibberish so no one else can read it? So here's our game plan. First, we'll talk about how cryptography is literally everywhere. Then, we'll get into the two big ideas behind it all. After that, we'll see the real-world solution that makes the internet work, peek into some future magic math, and wrap up with a quick decision guide for you. All right, first things first. Let's get one thing straight. This isn't just for spies and hackers, okay? Cryptography is a massive part of your everyday life, whether you realize it or not. So, what are we really talking about? At its core, cryptography is just the practice of using math to keep communications secure. But what does secure even mean? Well, it really boils down to four main goals, or promises. Okay, so you've got these four core goals. First, confidentiality. Pretty simple, only the right people can read it. Then, integrity. This makes sure the message hasn't been messed with in transit. Third, authentication. You gotta know you're actually talking to who you think you're talking to. And finally, non-repudiation. This is a fancy way of saying the sender can't later deny they sent it. These four things, that's basically the mission statement for the entire field. So that's the what. But what about the how? How do we actually pull all this off? Well, it turns out pretty much all modern crypto is built on just two really clever core ideas. The first idea is called symmetric encryption. The best way to think about this is a simple lockbox. You and a friend share the exact same key. You use your key to lock it, send it over, and they use their identical key to open it. Super simple, right? And it's incredibly fast. But there's a huge catch. How did you get your friend that key safely to begin with? If someone intercepts the key, your whole system is broken. And that problem leads us right to the second big idea, asymmetric encryption. Now, this is where things get really clever. Imagine you have a mailbox with a mail slot. Anyone, literally anyone, can walk by and drop a letter in. That's your public key. But only you have the one-of-a-kind private key that can actually open the box. See how that solves the problem? You can shout your public key from the rooftops. It doesn't matter, because only you can read the mail. So here's the big trade-off. We have symmetric, which is lightning fast, but has that key-sharing problem. And we have asymmetric, which solves the key-sharing problem beautifully, but man, is it slow. You can't use it for encrypting, say, a whole movie. So what do we do? Do we have to pick one? Well, how do we get the best of both worlds? The speed of symmetric with the security of asymmetric. The real-world solution is actually genius in its simplicity. We don't choose one over the other. We use both. They work together in something called a hybrid system. And this is the engine that powers pretty much all security on the modern internet. Your bank, your messaging apps, all of it. Okay, the perfect example is that little padlock you see in your browser bar. Here's what's happening in the blink of an eye. First, your browser and the website use the slow, clever, asymmetric method to do one thing and one thing only: securely create and share a brand new one-time use secret key. Then, once they both have that secret key, bam, they switch over to a super fast symmetric algorithm to encrypt all the actual data, the pictures, the text, everything. It's the security of one with the speed of the other, the best of both worlds. Okay, so that's how things work today. But what about tomorrow? Well, there's something on the horizon that honestly sounds like it's straight out of science fiction, but I promise you, it's real. It's called homomorphic encryption. Now, think about this for a second. With everything we've talked about so far, to actually use your data, to do a calculation, to read it, you have to decrypt it first. And that split second where it's decrypted, that's a point of weakness. Homomorphic encryption completely flips the script. It lets you compute on data while it's still encrypted. The data is never, ever exposed. It's kind of like being able to work inside a locked box without ever opening. And the implications of this are just massive. Think about it. You could have medical researchers analyzing huge data sets of patient records to find new cures without ever seeing a single person's private information. Or imagine banks teaming up to spot fraud patterns across their systems without ever having to share confidential customer details with each other. This isn't just security, it's true computational privacy. So if this is so amazing, why aren't we using it for everything right now? Well, One word: speed. Or lack of it. Right now, doing math on encrypted data is somewhere between 100 to 1,000 times slower than just doing it on regular data. That's a huge performance hit. So yeah, closing that performance gap, that's pretty much the holy grail for researchers in this field. Okay, so we've covered a lot of ground, from the basics to the far future. Let's wrap this up with a super quick guide so you can remember which tool gets used for which job. Think of it like this. Need to encrypt a huge file and you need it done fast? That's a job for Symmetric. Need to share a secret key with someone over the internet safely? That's where asymmetric shines. Need to digitally sign a document to prove it's really from you? You'll use something like RSA. And what if you need to process data that you're not even allowed to look at? Well, that's the magic of homomorphic encryption. And that really leaves us with a final, pretty big question. As this magic math gets better and faster, we're heading towards a future where we might not have to make that trade-off between privacy and utility anymore. So what does a world built on true digital privacy actually look like? What kind of amazing things could we build if we never had to worry about our data being exposed?